Again, I'll refer to the documentation that's available on the Spark website. So we'll be covering critical concepts related to what's an RDD, how does it form, the operations that perform on top of it. We spoke about cache persistence in the concluding part of the previous video, and then we'll talk about the how to exchange information more generally between executors and driver as well. So for this, I'm going to go to the Spark RDD programming guide website. So these are internals for the most part. I'll tell you that for typical analysis, you would not use RDD interface. You will actually use the data frame interface, which we'll cover in the next subsequently. But it's important to understand what RDD is, how is it constructed, because the data frame interface also builds on top of the same thing. So like I mentioned before, RDD is basically the resilient distributed dataset. It's basically a collection of data which is formed as a result of an operation like a transformation, and then it's fault tolerant. That's why it's called as resilient. It's fault tolerant because any of those different stages can fail, any of those different operations can fail, and then you would still be able to reconstruct that particular dataset from its previous RDDs, from the previous RDDs, etc., the chain of RDDs. So that's why it's called a resilient. It's distributed because it's distributed across the cluster. So you're not limited by scale to a specific machine. So that's basically it. You can construct RDDs from flat files, from various sources of data, it doesn't matter. Spark has libraries built for all of that. Great. So now let's looking at the operations which are possible. So there are two main constructs here. One is called a transformation, the other is called as an action. A transformation, as the name suggests, right, is going to take data from a particular shape to another shape. A shape means a certain form of let's say, rows and columns with certain values in it, to a different shape meaning different set of rows, different set of columns, different set of values. But at the end of the day, these are two data frames again, right, or data sets. Whereas an action returns a scalar value or a set of values to the driver program. So the input to the action is a data frame or a data set of a certain shape. The output is basically a set of values which get returned as a scalar list or a scalar array, etc., to the driver program, which then does further things with it. So the crucial thing to keep in mind is transformations always happen on the executors, which means they happen on the worker nodes. Actions, on the other hand, execute on the worker nodes, on the executors, and then the output is shipped to the driver program. So the output of an action is not an RDD. So which means if you do something on top of it, on top of an output of an action, it will not be parallelized. It would not be running on the executors, it actually runs on the driver. Go back to the Spark cluster. The visual you should keep in mind is the master node, which is where the driver runs, is just one in number. The executors, which runs on the worker nodes, are many. So the power, the parallelism, the resources are all available in the executors. The master is just one. So when you run your transformations, it runs on the executors, which is good, right? Because you get all the parallelism that you want. When you do an action runs on the executors and ships the value to the driver. The driver runs on the single master. If you do further operations on top of those actions, you're stuck with the driver program and the master node on which it runs. You're stuck with those resources. So the most common performance pitfall that occurs when newcomers come to Spark and start writing stuff is they think in terms of actions. They think in terms of all of these machines have to be equal. They're not, right? The actions are producing outputs which come back to the master, and then they do further data intensive operations on top of it. So the actions are meant to do small data output computations, right? Meaning the actions operate on large data, but when they ship data out, you're intended to actually either ship small amounts of data back to the driver, or if you're going to use an inbuilt function to write to a storage system like a database or a file system, then you can write large data sets also, not a problem. But then if you're shipping smaller values, then the driver program resources do not matter that much. But a common newcomer mistake is they use actions to ship large values to the driver, and then they do further operations on top of it. When that happens, it all runs within the driver program, and that becomes a performance problem. The second common newcomer mistake that happens in Spark is the operations, while they laid out sequentially, they are not executed in that order necessarily. So remember, we spoke about DAG. We spoke about how the DAG orders the operations into stages and then executes stages together. What it also does, it actually reorders operations at times, right? So what this means is, when you specify a Spark program, you're not necessarily specifying the order in which it's executing. You're only giving declarative direction to the sequence of operations, whereas the actual sequence of operation that executes is determined by the DAG scheduler. More importantly, when the operation, when the Spark program is compiled, when it's run, the sequence in which the operations are performed is determined by the DAG scheduler, not by the order in which it occurs in the program, right? So, while you lay out the program sequentially, and we are used to reading, and we used to, like the Python model of operation or the Java model of operating, we used to reading sequentially in procedural programming and thinking that each of them gets executed one by one. In Spark, that's not the case, right? So that's a very important difference as well. So what this means is, the way you think about variables, the way you think about storing temporary state has to be very different compared to how you would think about it in pure procedural programming. So I'll come back to that a little later. So let's take an example of a Python program. So here the data is available in data.text, and I'm using the text file function to read data from there. At this stage, the lines RDD is not actually created yet, because what I've done here is just a simple transformation, right? So the lines RDD is not created yet. In fact, when the Spark program executes, none of this executes upfront. In fact, there is no action as we see in this example. So lines is an RDD that gets created, and then you perform another transformation on top of it. Like in this case, it's a map function. The map function in general. So by the way, the map and reduce here are not the same as the map reduce that we saw in Hadoop. If you just look at it precisely, there's a slight nuance here, but nevertheless, the map here operates on a per row of data. And what does it operate? It operates a function. The function, I'm just going to use lambda syntax that's there in Python. So I'm going to use a lambda function here. All it's doing is just I'm replacing the row of data with the length of the row, right? So here these are text files, basically lines of text in a file. So I'm taking the line that I've read today, rather at this instance, and I'm replacing that with the length of the file, the length of the line rather. So the input RDD is a bunch of text. The output RDD is the same number of lines as the input RDD, but then instead of each line of text, I have now the length of the line. Then I have a reduce operation, which operates on top of the line lengths RDD, and this reduce operation takes multiple elements of the line lengths, right, which is basically multiple lines, and each line is, like we saw before, is just the length. So all I'm doing is just a custom function that says I'm going to sum up both of these elements together, and this reduce function, this reduce operation operates on all the elements in that RDD, which means what I'm effectively computing is the total number of characters. Why? Because I take each line length, and I'm summing up all the line lengths for all the lines. So finally, what I have here is basically the value, which is the total length of total character count of that particular file. Sorry, I was mistaken a bit. The total length is actually a value. So this reduce is actually an action, right? So the action operates on an RDD but produces a single value. That single value is returned back to the driver program as a variable. So the driver program can now refer to this variable and then do like things like printouts or like display it on the console and things like that. But if the driver program tried to display the line lengths as a variable, it wouldn't work because it's an RDD. The driver program does not have a mechanism to actually bring the data back in without performing an action. Okay, so passing functions, you can use anonymous functions, you can use your own custom functions, you can use lambda expressions. Does not matter. All of that is like regular regular work that you can easily do. But the most important thing to worry about is something called as closures. So here, because of the lazy computation model, there is no order in which you are guaranteed that the work will execute, except for the job that constitutes a set of transformations that lead up to an action. And because the execution environment is split between the driver program, which is running on the master, and the executors which run on the workers, there is no concept of a variable which actually transcends all of this in a seamless manner. So imagine if you had ignore Spark for now, right? Imagine you just had access to two different machines. One machine, you created a variable in a Python program. How do you get access to that variable in another Python program running in another machine, right? In fact, even within the same machine, another Python program cannot get access to this variable that's there in this Python program. That's very clear to all of us, right? I mean, we don't have confusions in that regard. Something similar is happening here, right? The driver program that running in the master cannot define a variable like how you would define a variable in Python and hope that the executors in the worker node have access to that variable. It doesn't, because for all practical purposes, these are two different programs running on two different machines. If you need access to a variable which transcends both these machines, you have to use special variables, right? Now that's point number one. The point number two is, for the executors to work, the executors need the code that need to be executed. The tasks are basically code. The code comes from the driver. So which means the driver needs to be able to ship the code that needs to execute to the executor in order to run. This code can be shipped only if the code is completely self-contained. The code being self-contained means it has access to functions, it has access to variables which are completely self-contained, which makes sense in that execution. So that is what is referred to as closure. So what happens here is the job which needs to execute, the task which gets farmed out to the executor, that task it gets checked for closure, which means it doesn't have access to the functions. The functions do not reference some global variables, or functions do not reference libraries which are not available in the executor. So all that gets checked, and when that check is successful, that's when the closure is deemed to be complete, at which point the code gets shipped as a unit of work and then gets executed in the executors. So if you reference global variables, right, then what you will find is when you try to run the program, the closure would fail, and as a result the error that comes out would be some cryptic error related to not having access to that particular variable. So we'll take the example that's there in the documentation. It's a very instructive example. So let's say I have an RDD which I've formed by parallelizing a bunch of data. The task I'm entrusted with is to count the number of lines or count the number of records in that particular RDD. So the naive way of going about it, which is a procedural programming way, is to initiate a counter, right? And the counter has value, let's say it's initiated to 0, and then I start to increment the counter, which is what I would do normally, right? Because the counter is a variable that I've defined at the top level of the program, I use that reference here. Let's say that that's a global declaration, and then the counter gets incremented by the number of lines of the sentence, right? The RDD, which is distributed across the executors, needs to have this custom function to be executed. So I use the for each special construct, and we'll talk about what the different functions available are, different map functions, different transformation functions exactly in a little later on. But I'm using the for each construct where I'm applying for each data element this function, the increment counter. What I want to happen is for each data element to be counted towards the total length so that I get the final answer, right? But the way I'm going about it is wrong, because I'm expecting the function to be executed in the executor, referencing a variable which is called as counter, which is initiated in the driver program. And for all practical purposes, these are two different Python programs running in two different machines. It's not going to work. So what you'll find happen here is, this will throw an error, right? In fact, if the counter is not, it's not instantiated. In fact, in this case, the counter, if you don't use a global declarator, the counter is locally accessed. Then the counter gets initiated locally by each of the worker nodes, and you might even get the wrong answer. The program will compile, you'll get an answer, but the answer is wrong, and that's dangerous. So be aware of closures. Be aware of the fact that whatever you need to ship to the executor, it's as though somebody is like shipping code over the network. So obviously the code has to be completely self-contained. So the functions, the access to references, all of that needs to be there. All right. So the other common way in which the newcomers to Spark have a problem, have a challenge is they typically want to try to look at elements of an RDD just to check whether the values are working out correctly. So the standard thing that people end up doing is something called as, printing the element of an array. Like in Python you would use println, right, or print. So here also that function is available. You could use for each and println, but what ends up happening is, notice that the for each is a transformation that runs on the executor. So the print ends up happening on the executor, not on the driver. So which means when you actually do this operation, you get all the outputs being printed to the local longs that run in the executor, whereas the output will not get shipped back to the driver at all. So you won't get any data in your console. So to be able to achieve what you wanted to do, right, which is the act of getting the data out and looking at a sample, you use what's called as collect, or you use what's called as take. So those are two functions available to you. Great. So more generally, let's take a look at what the different options available are. Transformations, like we spoke about, are the set of things that transform one data set to another, one data frame to another. When we look at Spark SQL, we look at data frame transformations that are supported, but RDD transformations are also broadly the same concept, right? So here, map is basically the most generic form of transformation. It operates on one data element at a time, and it invokes a function. The function can be custom, right? From custom function that you define. Filter is like basically being able to look at whether the function returns a true, and if it returns a true, then the data element is deemed to be successfully passing the function condition, and it gets successfully filtered in, as opposed to those which don't pass the condition and which get filtered out. Flat map is slightly, it's similar to map, but then it flattens all of the output elements to form a sequence or an array, as opposed to like multiple different data elements. So it's useful when you want to flatten out a nested structure, etc., or a collection of items into one item. Likewise, map partitions with index, sample, union, etc. You can take a look through the documentation, you'll understand more. Reduce is also a transformation, group by transformations. Reduce by key is basically saying, reduce by key is exactly the same as reduce in MapReduce, but here you are saying that I'm going to reduce based on a particular key. The key is determined by the key value pair in the RDD. The RDDs, these are special RDDs which have a defined format of key value. So the reduction automatically gets applied on key, and the values get operated on by the function. Aggregate by key, sort, etc., join, all of these are interesting concepts. Co-group is basically when you take two RDDs and you want to join them together, right? And when you join them together, and these are key value RDDs, you want the key to remain the same. Basically, you want to join on the key, but you want the values to be accumulated together. So in this case, for instance, the RDD1 is partition K, rather RDD1 is formatted as key value KV. The RDD2 is key value KW. You want to form, you want to have the ability to iterate on all the values of V and all the values of W for the same key. In which case you can use co-group instead of a join. So all those elements get brought together based on the key, the value of the key, and then the values themselves are available to you as two different iterators, and then you can iterate on them to do some common operations. And this is a more efficient way of doing custom unions of values for the same key as opposed to doing a join. Alright, so all of these are transformation examples you can take a look through at your leisure. Actions, on the other hand, like we spoke about, take an RDD or take a data set and then they perform an action which produces a value which is not an RDD. Like usually it's shipped to the driver program or it's written back to like a storage area or a disk. So here the most common action is reduce. So it takes a function and which gets applied on bunches of arguments, like bunches of data elements, and then it produces like a cumulative answer or it produces a final answer. Collect is one of the most common things that you would use to collect a bunch of data from your RDD, from your executors back to the driver. Count, first, take, all of those are very, very standard examples. The more common functions that you would also use would be ways in which you take that same data and you store it back to a file system. Right? You save an RDD as a text file, you save it as a sequence file, save it as an object file. In fact, there are other variants of this which save to a database, etc. etc. And then the last element is basically for each. The for each is actually going to go run through every single element in your RDD and then runs a function. And then usually the functions that occur here are wanting to do per element operation, which are equivalent to doing actions equivalent to doing actions on each of those elements. So that's what the role of the for each is. Okay, so with that, I think we are through. So the next topic that I wanted to talk about is the variables, right? So the transformations and actions give you a mechanism to actually give you various data processing capabilities using functions that you can define for yourself. But remember, we spoke for the closure to make sense, the variables have to be special variables, right? Those special variables are what's called as broadcast variables or accumulators. So those are two different options available. Broadcast variables, as the name suggests, are variables in a conventional programming context, which are explicitly broadcast across all of the executors and all of the driver, and the driver as well, so that all of them have the same shared copy. Effectively, it looks as if they have the same shared copy. In reality, you have copies of these variables across each of those different caches as well as in the driver, and then Spark is responsible for making sure that changes in one gets propagated to changes in all. Right? And if that propagation fails for some reason, then the operation itself is failed, and then the application fails. So Spark gives a guarantee that the broadcast variables are always in sync. So naturally, you do not want to use broadcast variables for as a concept for broadcasting large data, because then the task of keeping the variables in sync across all of these machines becomes prohibitively expensive. So you want to use it for small variables, small lists, arrays, dictionaries, lookups, whatever. So that's one angle of broadcast variables. In effect, the broadcast variables themselves are actually executed using shuffle operations. So you can imagine it actually becomes very expensive if you use it for large data sets. And so that's broadcast. The way you would use a broadcast variable is just by declaring a variable v to be with the function called as broadcast. So in Python, you would just use it this way, right? Broadcast function, invoke it with a variable or with a very specific data set that you want, and what it creates is the broadcast variable, and then that broadcast variable can be accessed. The value in it can be accessed by just invoking the dot value. It's a special object. It's not a data frame. It's not an RDD, but you can refer this within any of the functions that you write. The other example of a shared variable is what's called as an accumulator. Accumulators are shared variables which have are like broadcast variables, but which explicitly only allow a very specific type of operation, which is called an associative accumulative operation, which is like an addition, right? So here the state cannot be modified directly. Instead, you allow you cannot update or overwrite the state. Instead, you use accumulator functions, like functions that are easily distributable and operatable as individual stages of operations without having to worry about number of data elements or number of executors. So you could do it 2 at a time, 3 at a time, 4 at a time, and that's up to Spark to figure it out. And the reason it would still produce the correct answer is because the operation that you perform is associated with everything. So that's why these are specially designated as accumulators. So very useful for doing things like counting and summing, right? So let's say you want to count the number of lines in the file, you could just use an accumulator variable. So the wrong example that we looked at last time around, the wrong way of doing things rather, which was using a global variable and trying to use increment within the for each, that wouldn't work because those variables are not accessible to all the executors and all the machines and the driver. Instead, if you use an accumulator, you could just embed the accumulator reference within that function and then add it, right? Add to it whatever you want to add, and that would actually produce the correct answer. In fact, accumulators themselves are special in another way. You could look at the value of the accumulators in the Spark console, specifically in the Spark UI as well, right? And this is useful for you to do things like debugging and understanding progress and stuff like that as well. Okay, so that's tracking accumulators. So there are more complex types of accumulators. I mean, you can define your own custom accumulator just like you define a custom object and things like that. So all of that is also possible. So with that, we've taken a look at some of the key internals pertaining to. So let's come back here. In the next lecture, we will take a look at the Spark SQL data frames themselves.